In this video, we'll continue our discussion of section 2.4 by discovering a method that actually would turn a differential equation that is not exact into an exact one. This will be done by multiplying the equation by an integrating factor. We don't know what this integrating factor is, so what we're going to do is try to find it by calling this integrating factor u. All right, so I'm going to multiply everything like we do for integrating factors. Everything is going to multiply by that u. All right, so m and then dx, then I still have that u here, times n of xy dy, and that equals 0. Okay, so now we're going to say, we're like forcing it to happen, but we're going to say now this is exact. We're going to assume that. The reason being, because if I assume it's exact, then I can work with it like it's exact and maybe try to find what u actually is. So if that's the case, then I'm going to go ahead and take my derivative of both sides. I'll do with respect to y of my m. This is my new m, by the way. Let's call it m star. And then this will be my new n, but we'll call it n star. Okay, so I'm going to take the partial with respect to m star. All right, so that's going to be, it's a product rule. It's kind of weird with respect to y. So I get u with respect to y times m plus u and then times m with respect to y. And I know this is going to be equal to the partial of x with respect to n star. We know these are equal because we assumed that the equation was exact. All right, so that is going to be ux in plus u in x. Okay, so I know that these two things are equal since the equation is exact, and I know that when I take that second partial, that the two phrases are going to be exact expressions. All right, so I'm going to set up that equation and get rid of all that extra fluff that's in my statement. Now, right here, we're kind of stuck. All right, we're going to have to make an assumption right here. So we want to, and we're going to make this assumption later as well, and we'll get two equations from this. So I'm going to assume that u of xy is really just in terms of x. Okay, we're going to assume that. We can assume the x one as well, and that's how we're gonna get two equations from this. So I have that. If that's the case, then anything with respect to y is just going to be a 0, right? Okay, so u of y is 0. So on the left side, I get a u times m of y equals, and then we still have this whole right side. There is no u derivative with respect to y. All right, if I have that now, then I actually can move things around. Notice that I have, I can do u of x by itself. Let's see. Yeah, let's do that. So I'm going to pull this u of x. We're going to leave that over there on the right, but I'm going to flip the equation. So I get u in y minus u in x, right? And that's what yes, perfect. Okay, so notice now that we have this um, u and this on both sides, my minus nx. There's a common denominator, common factor of u. And then I'm going to go ahead and just solve for u. And then let's state a few other things. So ux is equal to du dx. Since it's only in terms of only in terms of x, then I can use normal derivatives. All right, so if that's the case, I'm going to solve for this, and I get u equals du. Let's leave that actually. I'm going to leave that off to the side. So if I divide by, let's see. Oh, actually, hold up. So we have that. I'm going to go ahead and replace everything. Du dx times n equals, and then it's my minus nx, and that u is still there. Now I can get to du dx by just dividing by m. So I'm going to get this here my minus nx over n times u. Now I'm going to add a page. I'm sorry. Hopefully you just can add your own page. I always have people in class get frustrated with me with that. but it is what it is. All right, so, oops, let me move that down so I don't lose it. I don't know why that didn't go with it. Okay, so keep going. This may seem weird here. Like, how do I undo that? Because I can't really, I don't want to do the derivative of u because this is just going to spit out another, like, what do I do with this, right? So instead, this is hidden. Maybe some of you guys seen it. I'm going to move this whole side over here. Times u, and that equals 0. I want you to notice it's kind of hidden. That is first order linear. All right, it's the same thing that we've been working with, right? U prime and a u, and then everything else doesn't have a u in it. So that means that this u then, or the integrating factor in this case, would be, let's call it a mu. It's really called u, I guess, in this case. It's going to be e to the integral of my minus nx over n dx. Okay, so there is a rule here that if it ends up being in a certain way, then we're going to use one, and then we'll actually have a second one. If you know how we assumed u of y was, or u was just in terms of x, we could also solve it only in terms of y as well. So we get mu of that one to equal that. And then mu of this one, okay, this is, I'm just going to give it to you. If you'd like to go up and work it out again and let u of x equal 0 this time, then we're going to get, let me make sure I write this down right, nx minus my, and then now it's going to be over m instead, dy. All right. If this statement that we just came up with, my minus nx over n, is in terms, is in terms of x only, then use above. Okay, I'm going to put that all together. So we have this. So this is our statement here. If that's our multiplier, if the thing in the exponent there is in terms of x only. All right. And then we're actually going to have that same thing. Let me erase some things here. Okay. If this thing, the other one, nx minus my over n, is in terms of y only, or is it x only? Yeah, y only. Then we're going to use that second one that's there. So we're going to have to plug it in, and then we're going to have to check it to get the right stuff we need. Oh, that's not a highlighter. That's why I couldn't find that. It's looking for purple. All right, so they're two different things. You're going to have to check. Sometimes you'll check both of them because you'll do the first one and it won't be in terms of X or terms of Y only. And then um, you'll check the other one and it will be, or neither one of them will be, and then you won't have the method to solve it as of right now. All right, so now that we have those, let's go ahead and try one of these. All right, so starting off, m of how it's set up. First, I'm going to check to see if it is exact. 3xy plus y squared, because if it's exact, I can stop. My then is going to be a 3x plus 2y. N of xy is the other thing in front of dy, x squared plus xy. And then we do n with respect to x. Remember, the reason this works out is because they're actually truly double partials with our original function. So 2x plus y, those are not equal, not exact. So therefore, dE is not exact. All right, so here's our attempt to make it exact. We're going to try, first we just plug these things in, my minus nx over n. I'm going to start there, and if it's in terms of x only, then I'm good. If this isn't in terms of x only, then I would try the other one to see if it's in y only. If it's not, then we have to stop as of now. All right, so I'm plugging all this in. Okay, I got my is 3x plus 2y minus, and then minus 2x and minus y. And then put this over n. N was x squared plus xy. Just to tell you a common mistake I see here, because I make it sometimes, for this thing here, I was grabbing, sometimes in my work, I would put this function here. Just be careful that that on the bottom is actually the true n, not nx. All right, so notice on top, let's combine like terms. It looks like I get x plus y. On the bottom, notice there is a common denominator, x plus y, or x is the common factor. Sorry, forgive me. X is the common factor between the two, and then this actually works out for us to get a 1 over x. So this is what we want to use, is that our mu that we're going to multiply in this case, or e, or u, I think that's what we called it last time, is going to be e to the integral of 1 over x dx, which is actually e to the ln of x, which is just x. And its absolute value, if we wanted to go that far, we're just going to leave it alone. We'll be okay. So that's what we're going to multiply our diff e to, our original diff eq, multiply it by x, and then it should be exact. So let's go ahead and do that. We get 3x squared y plus xy squared dx plus, and then x cubed plus x squared y dy, and then that's still 0 on the right side. So now I want to check to see if it's exact, but let's not call it m again, let's call it m star, because it's not the same. That's math me, Karen. And then we have m star y. So we get 3x squared plus 2xy. Okay, n star, not the same as n, it's new, is x cubed plus x squared y. And then n x of x n star, all right, is going to be 3x squared plus 2xy. So now DE, therefore DE is exact. Okay, we'll have to keep working. They want us to solve it, not just make it exact. So now that I can do that, then there exists an f such that when I take fx, I get m, and when I take fy, I get n. So I can find that f of xy by integrating m with respect to dx. So that is the integral of, oh, m star, forgive me. This is m star, n star. All right, I'm going to replace it. So we get 3x squared y plus xy squared dx. If you haven't picked it up, I could have picked n star and do dy. I just stay consistent, helps me make less mistakes. So this is x cubed y. Up the new one, divide by, up by 1, divide by the new one. Same thing here. And I get 1/2 xy squared. And then this is plus h of y. Then I'm going to take, that's our calculated f. I'm going to take that with respect to y, which gives me x cubed. And then the 2 comes down, and I just get xy plus h prime of y. And then I'm going to set this equal to n star. So n star will be, don't take the prime, I get x cubed plus x squared y. Oh, I forgot to put a 2 right there. I was like, wait, what happened? The 2 cancels, leaving me a square. There we go. This cancels with that, cancels with that, cancels with that. This means h prime of y is equal to 0. That means h of y is equal to c. So I have enough information to write my answer. Here's my f. So x cubed y plus 1/2 x squared y squared plus, equals c. Remember, for exact, we don't put plus c and do an f. We just set it equal, because now that thing will be the equation that if I take the partial, I'll get the thing m, original m. And then if I, with respect to x, and if I take the partial with respect to y, then I get n, the original n. So there we go. There is our solution.